finite element analysis. Dear students, let us start with Module 2, analysis of bars. Analysis of 1D bar element. Introduction to one-dimensional elements. In this element, each node will have 1 degree of freedom, that is an x displacement. These elements are suitable for one-dimensional analysis. Thus, 1D element can be a line or bar or rod elements. So we have so many types of one-dimensional elements. The first one is bar element. It consisting of two nodes. Quadratic element, it consisting of 3 nodes. Cubic element, which consisting of 4 nodes. Again, the classification it will further continue. So among all these type of elements, every node it will have only a single degree of freedom. Example I have taken here, it is a 2-noded bar element. Each node it will have a degree of freedom 1. So it will have a single degree of freedom. That is, it will have a displacement of u1 at node 1, u2 at node 2. Displacement will occur along x direction since it is a 1D element. Since our syllabus it is restricted only to 2-noded bar element. So you have to analyze the problems using 2-noded bar element. So the first thing is you have to find out the strain displacement matrix for 1D bar element. So it is called as B matrix. Strain displacement matrix represented by, we have to derive strain displacement matrix for 1D bar element. Let us consider the bar element. It's a 2-noded bar element consisting of 2 nodes. At node 1, the displacement is u1. At node 2, the displacement is u2. Let us consider the node 1, which is located distance of x1 from the origin. Node 2 is located distance of x2 from the origin. The length of the element, which is given as x2 minus x2, the difference between the two coordinates. So this element, it is represented in Cartesian coordinate system. Similarly, you have to represent the element in natural coordinate system, so that is zeta. The value of zeta is 0 at exactly at center of the element. Towards left hand, it is -1. Towards right hand, it is +1. So at node 1, zeta is -1. At node 2, zeta is +1. Now let us consider the strain in the element is given by epsilon, which is equals to dou u by dou x. This equation, it is derived in theory of elasticity. If you not studied elasticity, just remember the strain along x direction, which is given as dou u by dou x. Now I will rewrite this equation. Just I will multiply and divided by dou times of zeta. Multiply and divided by dou times of zeta. On rewriting, so strain, which is equals to dou u by dou zeta into dou zeta by dou x. Call it as equation number 1. Also, the field variable u, which is equals to summation of n into u. But for 2-noded bar elements, which is defined as n1 into u1 plus n2 into u2. Since we have only 2 nodes, so we have only the 2 displacements and 2 shape functions. Where n1 and n2 are the shape functions for 2-noded bar element. The value of n1 is 1 minus zeta by 2. The value of n2 is 1 plus zeta by 2. So these are the shape functions which we derived in module 1. Now in equation 1, you need the term dou u by dou zeta. So you differentiate the field variable with respect to zeta. So dou u by dou zeta, which is equals to differentiation of this. Half it becomes 0, minus zeta by 2 it becomes minus 1 by 2 into u1 plus Again 1 by 2 it becomes 0. Differentiation of zeta is 1. So 1 by 2 into u. So which is equals to, so I will remove off. So u2 minus u1 divided by 2. So you got the term dou u by dou. Again we need the second term, that is dou zeta by dou x. So we know that the relation between natural coordinate system and Cartesian coordinate system, which is given as zeta is equals to 2 times of x minus x1 by x2 minus x1 minus 1. Now you differentiate this zeta with respect to x. When you differentiate this, we'll get 2 by x2 minus x1. x2 minus x1, it is nothing but it is length of the element. So it becomes 2 by L. Now you take equation 1. In equation 1, dou u by dou zeta into dou zeta by dou x. Dou u by dou zeta is u2 minus u1 by 2. Dou zeta by dou x is 2 by L. So you just substitute. So strain, which is equals to u2 minus u1 by 2 into 2 by L. 2 to it get cancelled out. So I will rearrange this minus u1 plus u2 into 1 by L. Now this equation I will represent in matrix form. So strain, which is nothing but 1 by LE. I will remove u1 and u2. If you remove u1 and u2, here you get the term minus 1 plus 1. So minus 1 comma 1 into u1 and u2. You expand this minus u1 minus 1 into u1 plus 1 into u2. You will get same equation. Now 1 by LE into minus 1, 1. This I'll represent it as a capital B. U1 and U2 are nodal displacement. It is represented by the field variable in matrix. So strain, which is nothing but B into U. Or in some textbooks, we use instead of U, they use Q. So strain, it can also be represented as epsilon, which is nothing but B into Q, where B is nothing but 1 by L times of minus 1, 1. So is the strain displacement matrix for 1D or element. Again, we can find out the stress matrix. So we know that stress by strain is equals to Young's modulus from Hooke's law. Stress is equals to Young's modulus into strain. So sigma, which is nothing but E into strain is B into Q, B into Q. So sigma is nothing but EB Q. So from this, we can find out the strain and stress in a two-noded core element.